So the fashion MNIST dataset was released by Ian LeCun. Yeah. So and this is profile. Um, so here's our approach. We define the phase computational results. We define our data and model, construct the learning model, define cost function optimizer, and next please. So while building our neural network, we follow a systematic approach, which we have laid down here. So for creating our computational graph, we set variables to store our input data as X and one hot encoded labels as Y. We set variables to store our network weights and biases. Calculate the weighted sum for each. We calculated the weighted sum for each layer and perform the respective activation layers specified in each layer. So and the next was to compute the cost function, just like we all know for regular machine learning. Write codes to calculate the accuracy of our models. So and set our learning rate. We actually varied our learning rate to get the optimal learning rate that gave us our result. So and then finally we wrote the code for the training step. So this is basically a more detailed overview. So we initialize our variable for the code session. We initialize our variables, create an instance using TensorFlow. We train our model, the graph of the training accuracy, validation accuracy, training loss, validation loss gains. Number of epochs. The training set for computer vision is usually very hard to train. So it actually took quite some time to get different iterations for different number of iterations that we chose. So my colleague who is going to walk you guys through the code implementation will take it from here. Sorry. So this is actually a rundown of all our what we did during our project.
Thank you. Okay, like my colleague has said, we worked on the fashion MNIST data set. So because of our time, I just need to just talk about the basic things that we did. First thing that we did was to import the models that we needed, TensorFlow. Then we imported input data. That's the function from TensorFlow, from which we were able to initially use one hot coding on our labels. You get. So by this one hot shoot, so our labels were already one hot coding. Next slide. Okay, then we now build the random images from the training set just to gain some intuition about what the data was about. So we call this function that was written, and it generates 10 random images of our training set and our training of our examples and our output. So let's move to the next slide. Then we did the same thing for the validation set. Next slide. And then for the test set. So the first thing we're supposed to do was to implement softmaps. Next slide. So basically, next slide. Yes. So basically, each of our data was Yes, each of our data was in form of an image. Yes. So what we did was each of those images we enrolled them into a vector of 28 by 28, like 784 pixels. So you enroll each of those images. So we had like 784 different features. But like we said, our total number of training examples are 55,000. So we have like a training set of 55,000 against 784. Next set. Next slide. No, go to the next slide. First thing we did was we worked an open source library. And in terms of we have to first build a computational graph, as we told last week, before we can run our session. So here we built our computational graph using X as a placeholder to store the value for our data. Then we specify this as known since we are going to be working with both the train validation and test sets, and we had different number of examples. So next thing we did was to specify a point where we're going to store our labels, which is already one hot encoded. Then we initialize our weights to 0. Then we also put bias to 0. Then we did weighted sum. Next slide. Next slide. Next slide. Then we did softmax activation. Then we used cross entropy loss, and we used our learning rate at 0.005, and we implemented our training step. Next slide. And after we did the computational graph, we now initialize all the variables that we had and run the session. Then this was the training step which ran for 1000, and we had our learning rate at 0.005, like I said in the last slide. So this was the graph of our accuracy, and we actually had an accuracy of 82.3 when we actually initially did. So this is the graph of our accuracy as we talked about. I think that was when we were at Cisco. Normally, we're looking to make sure that our training accuracy increases, like gets to the maximum, and make sure that our training loss actually reduces, because that shows us that our model is actually working. Next slide. Okay, the next one was the 5-layer model using Sigmoid. That was the next task we were supposed to do. We were supposed to build a neural network that had 5 layers. The first layer was 200, 100, 60, 30, and 10, which was the output layer. Next slide. This is the Sigmoid application function that we talked about. I think that the teachers explained to us about that starts from minus, from negative, and goes positive. So if you predict any value that, so we must have a threshold here that any value that is below like 0.5 we predict as negative, above 0.5 we predict as positive. Next slide. So yes, this is exactly the same thing that we did, but the only difference is that we had to initialize our layer. So the first layer we had 200 neurons. We did pretty much the same thing that we did. We completed our matrix multiplication, did our sigmoid function as we said. Next slide. Then did the same thing for the second layer, 100 neurons. Third layer, 60 neurons. Next slide. Softmax activation, then cross entropy. Next slide. Then we also plotted the graph that we got for our this. And next slide. I'm gonna increase your encryption when we do that. So next thing was to replace the sigmoid function with ReLU. Next slide. This is the ReLU function. So instead of using the sigmoid activation function, we just replace all of our sigmoid activation functions with the ReLU. Next slide. Then, as you can see, this was normally sigmoid, but we replaced it by ReLU. So that was just basically everything still follows the same goal that we're just trying to increase in accuracy. Okay? Next slide. So we did the same thing for each layer, ReLU. For each layer, we changed sigmoid to ReLU. Next slide. Next slide. So that's what we did. Did our cross entropy, used our cost function cross entropy. Next slide. And then initialize our variables and then run our sessions and teach the trainings. Next slide. Got the graph for it and we had 95% when we train it. Next slide. The next task was to reduce the learning rate. So we wanted to reduce the learning rate from 0.03 down to 0.000, sorry, yes, down to 0.0001. So learning rate decay, like to exponentially decay your learning rates, like as your stuff is going, to just reduce it, to just get an optimal value. Next slide. So this was just the only thing that we had to change. We had to introduce this TF.train exponential decay and set this value as 0.003. This is 2000 and use this function, which was the exponential function. Then we trained using the normal train function that we did. Next slide. Then, yes, next up was dropout. We had to implement dropout. Now, peak is probability that between 0.5 and 0.75 that the probability of a neuron will be kept after each iteration. So I think Lawrence told us last week or so, in which we specified some neurons which would actually be dropped out, dropped out during the training, just to build a better model. Next slide. So whether we drop out was nothing different, was not super different from the normal one that we had. We just had to put a step for our variable learning rate. Remember that our learning rate is no more constant, it's actually decaying. So we introduce a step for the variable learning rates. Then, Yes, then PQ value to specify the probability that the neuron will be dropped out. Next slide. Yes, so what we introduced was this dropout. So that here using TFNN to drop out, this was the layer, like layer 1, then this PQ value specifies the probability that a layer will be, that a neuron rather will be dropped out. Let's next slide. So this is basically that. Next slide. That was not what we did. There was nothing different. Next slide. Then with this, previous slide. Then with this, we're able to get 95, a little above 95. So then my colleague will explain the covenants that we use in order to get accuracy. Thank you.
Thank you. As I said before, after running all the tasks that we were given before, we now decided to put the last task, that was to run convolutional network, neural network. This is a bit difficult challenge because we were not taught in class, so we had to do a little more reading about it. So what convolutional neural network does is this. It's going to what we call feature extraction. We are going to have some feature, like you have a picture in which you have different pattern on it. So what that convolutional neural network will do is it's going to identify each. So after combining the pictures, it can now run another neural network. How does it do that? So we have a sensitive. The first example is 28 by 28 and is having only one color. That's it. So, and when we try and what we do is we try and flatten our data set. After flattening it, so we are what's most important is filter to define our filter. So our filter is like you are going to these are our image. The filter is going to take only a small part of the image. After taking a small part of the image, so he's now going to try to identify the features of the images in that particular part. So after identifying the feature, you are going to build a neural network that will identify the feature here. So after identifying that part, you are going to move to the next part. So the most important thing is your filter, and the first part that we run is our stride. That's one. That's stride 1. So the second stride, in which we are now going to, after identifying all those features, we are going to recombine them to using instead of using 1 now, we are going to be using 4. The matrix is going to be reduced to 28 by 4. So the next is to use sorry. The next slide I will try and get. So we have placeholder for our step. Then the first convolutional neural network, second and third. Then the last one is the fully connected layer. So we did the initialization of the variables. Next. Then this is where the convolutional network. This is the code for the convolutional network. Next, you didn't include the accuracy results of the last part. They got around something like 95. So,
what's the summary?
Okay, summarize.
I have some questions. After summary, like what are the challenges you guys faced, and what do you think the use cases for your project, and what would you like to work on after this?
Working on this MNIST fashion project was quite an exciting and a challenging one as well. So one thing we noticed about running our codes and all is that the data set takes quite some time for you to train your feet. So usually if you are using it might be a challenge for you work. Function is more real life implementation in the sense that it could be implemented in e-commerce websites. Applying people to just like celebrities, but actually fashion stylists to save money, just have a pattern or something, and then it will save you lots of cost and all. So that's
Okay, future work. What would you like to work on after this?
computer vision is it's the project is an exciting one, and aside image recognition, I want to explore deep learning for financial services rather. Okay, my personal project, that's one I would like to explore basically. So the learnings from this project will actually help me explore that, and I think I can work with my team because the guys there were so amazing that they actually supported they actually supported all the way through to the end of the project.
Okay.
So yeah.
I don't think you guys introduced yourself. Let's meet you.
Oh, okay. Here's the team. Sorry, some other guys were not added there. That's me over there. Femi, where? Yeah, that's it over there. Leroy. Is Leroy here? Okay, he's not here. Ubon. That's him here. Festus. That's an amazing guy. Oliver. That's him at the back there. Clinton is not here because of he has to put his hands. That's Victory. And that's Abdulaziz.
Please,
Right?
guys, give them all a round.
Thank you very much.
Okay, group. The next group should please come set up. You have 15 minutes, but here's how it works. You should be done by 30 minutes, so you can take 2 minutes to answer questions or anything. Yeah, we didn't ask anyone if you had a question for them. Okay, so there's a question for you. Okay. Can you give me a mic, please? Okay. Okay.
Yeah, that was filter. So we keep increasing the filter for that. So we have for each we are so now we do the inside of the filter.
So what happened? What happened? Hey, apologies on the delay. We're having a slight issue with HDMI cable, so please bear with us. Thank you.
Okay. That's it. Enjoy.
Hello everyone. Hello everyone. Good morning. This is group 3. So we are presenting now. Okay. Fine. Next slide, please. Okay. So this is just an outline of our presentation. So next. So introductions. Okay. So the group leader for our actions. Okay. So the group leader for our group is Adna. So he's the one behind the system right now. Then my name is Abdullahi Akindele.
My name is Dagger.
That's Abibola Emi. And so let's move on, please. I want to take it back a little bit. Let's talk about the history of AI. So for most part of history, AI has been shrouded in mystery. But I think the major turning point for AI was during the World War II when Alan Turing was able to build the Turing machine to decrypt Enigma. Next slide. So, okay, so AI is a superset, is the superset of machine learning. While machine learning is a superset of deep learning. That means under AI, when you go deeper into AI, you enter machine learning, then deep learning. So let's go next one.
Okay, so basically what it's talking about is that artificial intelligence is like the big subset of big universal set where we have machine learning and deep learning in it. So basically artificial intelligence, what it does is it tries to interact with the human, tries to act like the human and think like the human. Then the machine learning is, it enables the computer to think, to do things without being told to, instead of giving it instructions, turn left, turn right. It thinks and finds patterns to a data, more like either structured or labeled or reinforcement learning. Okay, next slide please. Okay, so deep learning is basically just mimics the human brain, the user. So we're going to talk a bit about our projects. Next slide. Okay, so we're working with the Amnes dataset. What it does is tries to recognize unwritten digits. So the Amnes dataset has like 60,000 handwritten digits, where we have 50,000 for the training and 10,000 for the testing. So next slide please, brother.
Good morning once again. Now, so how do they attain this? If this was our gathering, we'll say we did magic, number Esperito and this. But no, we started this squad together, so we know better. The only one we waived was neural networks. So what are neural networks? So neural networks contains layers of interconnected nodes. Each node is a perceptron and is similar to multiple logistic regression. The perceptron feeds the signal produced by multiple regression into an activation function, which is this, and this is the what? This is the output next. So when these layers are stacked together, it is called what? A multiple layer perceptron. Next. So first of all, we fed our input data into a what? Into a single layer network, and we got our output. Next, so first of all, we got when we ran it through suspended epochs, and one epoch equals 500 iterations. So when we ran our output, when we ran our to suspended epoch, we got a validation accuracy of 93%, and this is what this is the plot history, and we can see here it is the. From the train loss, we can see it is almost turning to a straight line here. That means what it is. Okay, thank you very much. It's almost coming to a straight line. That is, it is attaining its peak. Next slide, please. So we got an accuracy of 90%. Then we increase the added and hidden layer flows. We use signal activation, and what for the hidden layer, we use software activation for the output layer, and this is the plus history. We got an accuracy of 928%, and a test accuracy of 90% still. Next slide. So we added more hidden layers, and what this is not a traffic coding. This is actually a ReLU activation function. So next slide, please. We ran it. You can see the plot history is looking abnormal. It's not right. So we got an accuracy of what of 0.9% and a test accuracy of about 80%. So basically, multiple layer perceptron is not good enough for image classification. That's why we introduced what convolutional neural network. So convolutional neural networks, they are similar to basic neural networks, but what's the difference? So this is an example of a picture of a dog being fed through a convolutional neural network. Next. So this is the input, and this is where the convolution, all this space is where the feature learning takes place. It extracts the features, the edges, the tones and everything, and this is pulling. What this guy output is a tensor. So this pulling, it takes depends on the pooling you are using. If it is average or max pooling or sum of the pooling, it reduces the dimensionality of the pooling. And after this, the tensor is flattened here and was passed to a fully connected layer. The fully connected layer is just like your multiple layer perceptron. Next slide. So how do we use, what do we do to the CNN implementation? We normalize our data, that's to have our test data. You know, the data will be in matrix, so we normalize it to have it between 0 and 1. We use one Earth coding. We had two convolutional layers with number of filters for the 30 for the first one, 15 second one, and the size of the filters of 5 by 5 and 3 by 3. We use max pooling. That is, it will take the with pool size of 2 by 2. With a pool size of 2 by 2, it will take the maximum of each pool size. We added dropouts with probability of 0.2% at training, and at when it is testing, it will be 1. We added 4 dense layers. The 4 dense layers just like the fully collected layer. With the first one with 128 neurons, 50, 25, and 10 for the last one, because the last one has the output between 0 and 9. We use regular activation, signal activation for the output layer. We use Adam parameter, and the loss is categorical entropy, because this is actually, we are using one coding, so we will be using a categorical cost entropy. We fed it in batches, 200 by batch, and accuracy. So we got 99% for our conventional network. Next slide. So our model is not perfect, because we tested it against using external data. That is what the normal Google. When you go to search on Google, you search for number 7. The number 7 you get, which is really a big one, it's not perfectly with that. But when you test it, it's what's handwritten data. The one you get to write it to your hand, it's not really perfect. Well, it don't really work well with that. So actually, we are going to make it better probably after this, but this is actually what we can do for now. So
everything we've done so far was done using cloud computing, which was from Google. So basically, we ran most of the multiple layer perceptron using TensorFlow and Keras for the convolutional neural network. Everything was done on Colab. You know what Colab is, right? Like a Jupyter notebook on the cloud. That's exactly what Colab is. And the Colab was powered by GPU, like Google's free GPU, so we're able to harness all of that. So we have something to show you people. Number is which that would be the number.
Okay, basically, as I said before, the project, the model is not correct, it's not 100% correct, even though it gives 99% accuracy. So we developed a Flask project, deployed it on Google Cloud Machine, and we have some test data. Alright, so let me try opening the image. Okay, so basically, as I said before, if you use handwritten images, we get notice that some of the model doesn't perform properly. But when we use digital images from Google, like number 5, number 7, we get that the model can properly classify it. And another way of improving this model is if we can test using image augmentation. That's if we during training, we try to use random brightness. That we tell Keras that okay, don't look at the brightness of the images, because one thing that we've noticed is that if it's an image that is well lit up, it tends to perform better than normal images. Alright, so another example is okay, so this is number 1. Okay, so another example is number 7, for instance. Okay, submit. This is it as number 1, and if you go to this is number 7 here. Number 7 here, image from Google. It doesn't classify, so view for another one. Let's say number 9. Yeah, G's value is 9. G's value is 9. So long and short, depending on how the training is done, we believe that there needs to be, apart from just getting 99% accuracy, we also need to factor in some other things like how the image is going to come into play. For instance, like we're going to use it for, assuming we're going to use it for deploying, for instance. Now, what we'll have here is it's not going to be a placeholder where we upload files. What we have here is just going to be a box where you can draw numbers. If you draw the number 5 and you pass it to the model at the back end, it's going to classify it correctly because it's seeing it as raw data. There's a lot of noise in this kind of image files. Okay.
Okay, so at this point of time, we want to say a very big thank you to AI6 Saturday, to Kwan Yedi for hosting us here, and Auntie Tejo, and all the
I'm sorry. What was your name, please?
Sorry, my name is Ravi Prakash.
Raji.
Ravi.
Okay, Mr. Raji Prakash.
Ravi Prakash.
I don't know. Okay, just help us with Google and Uncle.
Okay, so I want to tell Google a very big thank you, as well as Kwan Yedi, as well as everybody here for coming and watching us and listening to us present.
So, Mr. Raji, do you have anything to say
Mr. Ravi Prakash.
Mr. Plakat, do you have anything to say?
So, I want to tell Auntie Tejo, thank you very much for...
She's not an auntie, Uncle. She's not.
Okay, thank you, Sister Tejo, for hosting us and bringing ISAC to Lagos and having us here in this court.
Google Developer Africa.
Okay, then I want to thank Google Developer Africa. Google Develop Africa, thank you very much for hosting us. Once again, I'm not thanking
Uncle Anit.
And Uncle Anit. Thank you very much.
Not Anit. Intel AI.
Okay, then Intel AI, thank you very much for hosting us and
Vespa NG.
Once again.
Those people watching us.
Yes, and our listeners, thank you very much for watching us.
Our AI instructors.
AI6 instructors, thank you very much.
You have to mention their name, Lawrence George.
Okay, Mr. George.
Not Uncle Mr. Lawrence.
Okay, Lawrence, George, whoever,
Tola, and Tayo, I think I know
Mr. Tayo,
mention Tejo again.
Tejo
Afonja.
Tejo Afonja.
Afonja. No, Afonja.
Tejo Afonja.
Alright, so any questions for them before I ask my own questions?
Any questions, please?
I have a question.
Okay, he has a question.
So why did you guys add Softmax at the output layer? Why not something else?
Actually, for multi-classification, Softmax works better than the other one, than the other classification, because Softmax is much about something about multinomial. It deals with multinomial, so it takes all the probability into consideration. It takes the main probability of the main one you want to use divided by the sum of all the probabilities.
Thank you.
Yes.
Okay, so like how were you able to, like how many convolutional layers did you?
Two, precisely.
And you had dense layers.
Yes.
So like how were you able to transition from convolutional layers to dense layers?
Actually, we used layers. So it's layers. We can when you are calling layers, we can just call. You can call when you call this, you can call the conv2 layers and I think class.layers.conv2. I said when you are using chaos, you can call conv2 layers and you call the dense layers. Before that you flat it, then you pass it to the dense layers. Yes.
Okay. So any other question?
Any other question, please?
So I have a question like, in terms of application, use case, and all. So what are the use cases for your project?
I think my team will say something about that.
Just like you said, we just want to work on it, and do something for the client. Like something like you can just write on
You understand? And it tells them what you can use it for learning, for training the blind. You understand? We are trying to look for a way we can add that to that kind of education for the blind.
Another question is.
Okay, you got 99%.
Yes.
Like on what subset of the data set?
What was it? We tested the data set in full, not in batch. The test data,
Calm down.
you passed it in full, not in batches.
Like how many test data? Like how many?
And the test the
For your first accuracy.
Maybe when
Challenges you guys faced.
don't know how to work offline. That is so. But for once, what we need is what the first thing is what I have to thank. I think whatever and Simon did the telephone numbers. Details. I have great teammates. So we never met for once. All we did was alright. And yesterday night when we finished everything else, we slept by 5.
Wow. This morning.
So we got, and it was offline, and it was like, we got overnight, everybody in the system, when your system records some users, when you tap some phone, and that's just one of it. That's just the video one.
Wow, awesome job, guys. Can we all please give them a round of applause? Thank you so much for the presentation. Thank you. So, next. So you can't
I
talk.
forgot to tell something. Mr. Lakon, sitting down the back. Thank you very much for your assistance.
What I would say is that this is awesome. You guys are going together the cohort. We have 5 more weeks to go, by the way. So we can have a group presentation. Like at the end, if you have anything to present, you can always make that happen. Something different. You get it. Adnan. I was really looking to say that. And that's also for every group, by the way. Like something practical, something we did not ask you, just do something. This is good. Please, guys, welcome to one as they present. What? Oh, 6. They have a name. 6 says group plus group.
Everybody, this is the 6th Sense group, and my name is Olatipo. Over here is Ife, and that is Jennifer. Then here is also a team member, Ibrahim Ghana.
Are you shy?
Yeah, fashion is image visual music for us. Yeah, what's meant? What MS do you have to say? MS is Modified National Institute of Standard Technology for Database Movements. Yeah, MS consists of 60,000 training data sets and 10,000 test sets. And these are images, they're in form of images, and they are in 28 by 28 pixels. Okay, MNIST consists of handwritten digits. MNIST, because fashion MNIST is like a direct replacement for MNIST, which is more complex than the normal MNIST. MNIST is overused already. MNIST is overused, it's too simple, it's for the faith added. Like, it's just too easy. So once you work on more complex, and so MNIST cannot be for computer vision, like as you can see, many good ideas will not work well on MNIST. If there's many bad ideas, they work on MNIST and not transfer to real computer vision. Alright, MNIST is like a benchmark benchmark for validating algorithms. If it doesn't work on MNIST, it will not work at all. But if it works on MNIST, it might still fail. So it's not certain that it's going to work. To the next slide. Okay, our solution is going to be according to application, the item, fashion item. See the blue bar is showing you the accuracy for each after it has been trained. So I want to tip off.
Alright, so we just run through the Colab session. So we actually implemented using the Google Colab through all of the step-by-step implementation, right? So just to do a quick introduction why this comes up. Essentially we have training examples, 60,000 training examples for our image. For our image training sets, then we have 10,000 examples for our test set. So however, what we just try to do is we try to, okay, this our implementation is done with Keras. So can you run through? So our usual suspects, the second cell, import non-parallel library. Then of course the PyPlot, for visualization, so matplotlib. So please just run through it. So the usual suspects, then here we just simply imported our data set from the Keras library within the TensorFlow, just so we can have our train images, train labels, test images, and test labels. So that was essentially what we did, just to separate the different image classes. Say, okay, let's have our train and let's have our test. So the image training sets, then the labels, which are the classes. So please, now here you see that we defined labels. So essentially, with MNIST, it's always 0 to 9 classes. So it's the same format that this fashion MNIST also follows. Now we have 0 to 9 classes. So within our classes, we have these different fashion items, like your t-shirt, top, the trouser, pullover, dress, till the end. If you count them, you see that here is starting from 0, then this is the 9. So 10 different classes. So those are the, can you run off? Can you go off? Then run the cells, run the cells.
Like run all cells, right?
Yeah, run all cells. Run. So, okay, let me just be talking through what we did step by step while the code runs. So the training, your image is just a visual thing, just to get the shape and everything. Then please go down. So then data preprocessing, just to have an idea of how our images are sort of classifying. So we entered like one particular training example within this using the matplotlib, just to have a visual classification of okay, what this image is like. So that's what you see under here. Please can you scroll up. While it runs, I'll just explain the results that we get. So the trained images, so usually in the RGB scale is from 0 to 255. So essentially, our training images, we just simply split it by that range to have between 0 to 255. And the test images as well, so just so we can have them in that format. However, okay. Okay. So what we did essentially during this project, I don't know why it's this low, I don't know which. But what we did was, we have the 28 by 28 image scale. Then if you look at the training examples for the training set, which is about 60,000, we have 60,000 examples. Then we have it by 728 pixels. So which essentially means that for each image, it's 28 by 28. So you get 784 columns for the training set. So then we try to flatten that to have just to work for a single row. I mean, to become like a row vector. So we can have like 1 by 7.8. Can you run down? Sorry, just run down. Sorry, is that the network is really bad. Okay, so some things are running, some are not running. Is that the case? Alright, so wasting there. Can you go on? Some cells are running, some are not running. Are they? Okay, now for this one now, we just wanted to have a visual understanding of what he was predicting. This looks more or less like a shirt, am I right? A sweatshirt. So this is like just to input a particular example into our model and see what it outputs to us, right? Randomly. So can you just okay, so now here, what we did was essentially to plot, like to make a plot of 20 different training examples. So let's just have them at random and let's just see what they would be outputting to us. So these are the different examples we're able to get just using the peak size and the range for you to look through 20 different examples and output the different results to us, right? So please can you scroll down? So we can see how it's classifying some of ankle pullover and the other classes of examples we have. So here was simply where we now needed to start preparing to build our model. So we didn't we had a classifier here. So within our classifier, we simply just we had to flatten our input share. So it's like the neurons about 128, right? So 128 input layers into like so then we have an activation function of ReLU. That was what we simply applied. And our output classes is 10, just output 10. Then using the softmax function to be able to get those appropriate outputs. Next step. Then what we used for our gradient descent was the Adam optimizer. The Adam optimizer is like the most efficient optimization technique to ensure that we are able to achieve what we call the gradient descent, to be able to converge at a much better and obtain the most appropriate optimal parameters that will give us the lowest objective function for our model. So loss is the cross entropy loss, which we are very used to. So we just call the library to help us generate the loss and accuracy. So if we run down, we see how it's training accuracy example. So over 100 iterations, right? Then we're able to get an accuracy of 95%. Then with loss of, can you check the loss of 0.1? You can see that 0.11. You can see the loss decreases as the accuracy increases. So that's what we have. Then, so now we just simply compare our model performance on the test set. So when we now simply pick the same model, we now simply just run it against our test sets, and we're able to get an 87.7% accuracy of actual true predictions. So then the next thing is to try and predict text images. So we came up with just a single image. So you have like here, what we just simply did was to for a particular test image, just input like a value of a particular class, then we have different predictions for that value there. So can you scroll down? Then add max. Okay, this add max is just like to find the maximum position of whatever output. What's the maximum? Then the output that is run through. Okay, then right here now, what we just simply did is to build a function that would have our prediction arrays. Then we now simply plotted it as an image to say that okay, if it's correct, if it's a correct prediction, it should be blue. If it's an incorrect prediction, it should be red. So we give the NP of max prediction array to get the positions, the maximum positions for each prediction. Then we now simply have the prediction array and we're able to output this plot to say predicted label and true label. So the predicted label will be red if it's predicting a particular example as wrong, then it will be red. If it's right, it will be blue. Scroll down. So here we see an example. This predicts with 100% accuracy that it's a shirt. And if we look at it, pretty much it is a shirt. So it's predicting correctly. And it's a blue bar. So it's predicting correctly. So can you scroll down? That's for one example. Okay, so here, it actually did not predict this correctly. So one of the issues around the model, it's not always like the most efficient in terms of predicting the most accurate. So it's classifying some images because we were still training and this was predicting it wrongly. It was guessing that it's a sneaker, but then it predicted sandal, which was 100% wrong. Just go down. Alright, so here what we're just simply trying to do is we try to, okay, now let's see, we have number of rows. We want to see 8 rows and 3 columns. So we want to predict within a range of number of images within our training. Then within the training examples we've actually modeled. So we just enter the number of rows and we now try to outplot our prediction against the number of iterations. Then we're able to get the predictions and the test labels. So those labels are those classes. And this is what we now have. Output and everything. Just scroll there. So you can see that it's predicting all of this. Output 100%, pull over 100%, share 100%, trust 100%. Then the example is misclassified every time. So it's not always like, at least it should be reasonably most efficient, but it doesn't mean that the machine cannot still misclassify or something. But we're trying to train and improve on the existing model to ensure that, okay, we're able to get as minimal as possible the lowest classification, misclassification rather. So, scroll. So this just to show us the shape of the image for our test set 20 by 20. Then eventually, all we just try to do is these are now on the test set, so we just try and impute the test images and try to predict a simple image. And scroll down. This is like gives us a wide range of, because it's more or less like a list. So we're able to get, even though we imputed one example which is predicting accurately as ample rows, it still brings it out as a list. And so the plot is more or less like showing it as for the list of classes that we have, you know, when we define our labels earlier. So that would be, please can you. So for now, I'll just hand it back to Ife to take us through the rest of the slides. Ife.
Automation. Our model, partial differential. I will have other optimization algorithm, the other graph, the other data, the stochastic gradient descent. Okay, and the one we made use of in our implementation, the Haddam optimization algorithm, which is adaptive moment estimation, and it works well in practice compared to others. It converges very fast. It helps us in vanishing. It helps us reducing the vanishing learning rates. So it deals with the problem of slow convergence or high variance in the parameter of the 3 to fluctuating rows. Yeah, learnings and takeaways.
Let's take a just quickly, so
What we learned from the entire process. We initially tried doing it ourselves. We found out that Keras helped us simplify the entire process. We see that it was very clear and simple. It handles a lot of the complexity for us. Then as we trained university, we learned that as the loss decreases, the accuracy of the model also increases. Even though, as you saw, it wasn't fully accurate, there's some things we need to change and probably go on to make it better, but I think we got very good answer to start with. Then, I think we got very good answer to start with. Then, so we had challenges of downloading this dataset initially. We tried to get it ourselves in the beginning. We found out that Keras Library actually has the datasets inbuilt, so that helped save us a lot of stress. And Google Colab was really helpful because everything is in the cloud and we use their CPU, so it was really fast for us compared to CPU and VM. So compared to trying to do it on your local system using Jupyter Notebooks, that was really slow. And then we had a very wonderful team where we also woke up to the night. We stayed in the house more than we had fun with the late time. So, and I think as time said, we'd like to continue with this to work up on here and see how people can do better.
Then there was one other. Initially, we planned on using TensorFlow estimators, but there were loads of issues around it, and I'm hoping that I can still continue and try and crack that a lot more to have a better classification for our image or fashion lines. Thank you very much.
What was your best?
87.7%. 95%.
Why did you think that happened?
Why is your thing so high?
So high. So while training, we try to apply using the Adam optimizer just to try and have an optimal parameters to have the appropriate weight and balance that will give us a very good model. So that was essentially what we did. So we had the hope that, okay, because we had a very, very loss function, which is our objective function, and we had a very high accuracy, we were going to essentially blow away the test set, have a better prediction accuracy. But for some reason, that came out as, maybe because it's a fashion and it's a lot complicated. I don't. Maybe we will need to check the implementation as well to see how that works. Validation set. We didn't really apply validation set, but we just try to train and improve. Yeah.
So like when your validation starts reducing, if you start increasing in reality, then if it gets to a point that it starts increasing, then you stop doing it. So if you have things,
we have achieved. We'll try and work on that as well. Thank you very much.
I have a meeting member there. I can see that there's just a few. Maybe you should just so everyone can see you. Appreciate your effort. Okay, so yeah, thank you for coming, guys, and for coming to Super Academy. The next group is, how many more groups have not presented? Group, please, if you haven't presented, please raise your hand. Like the group leader, please raise his hand. Okay, we only have 3 groups that are presented. What are the group 1, 7? Okay. And what other group is available? Group 7, right? Can you present now. Okay. You're just two. Are you expecting to go over? No. Yeah, so what would you say? Okay, class of the day. So there are 7 groups, 3 as presented, and 7 weight score. So if you have 3 more groups, are they not here? Group 5 as presented. Group 1 as presented. What about group 2? I don't think we have group 6. Group 2? Group 2 will be the team next one. It's not What about group 4? Just group 4. Okay, okay, so we have 15 minutes, guys. Please group 4 should be set up so that they can present suddenly after. They will have
You want to sit?
7. And it should be feminist meters. So, our group members.
We are group 7. My name is there, you can't see it.
It was constructed by.
Please stop murmuring. I'm really sorry. Please stop murmuring. It's really distracting. Thank you.
So it was constructed by the National Institute of Technology. That's why it's named. The name of the dataset comes from modified MNIST or MNIST dataset. And each image is 28 by 28. That's 74 pixels. And there's a standard split of dataset where we use 60,000 images to train the model and 10,000 images to test the model. So these are basic definitions. In neural network. Have the perceptron, connection weights, biases and application functions. This is the dataset. Visualize an example of the dataset. So this is for the number 8. You can see to form the 8, 28. And a neural network overview of 9 has 15 neurons, interlayer 15 neurons, interlayer 200 neurons. So this is the output of the neuron, and it has a cell body, the activation function, synapse, the axon from neuron, and drive. Output also. So this use these different activation functions to get an appreciable accuracy. Use CNNs, ReLU, softmax, sigmoid, and we also use forward and backward propagation. So when we use the softmax activation function, we got a test accuracy of 81.12. The definition takes vector of arbitrary value, tries to force it between 0 and 1. And this is the sigmoid and the ReLU activation function that tries to force it between 0 and 1. And hyperbolic tangent. And there's a relationship between the sigmoid function and the hyperbolic tangent, that formula. And then we use the sigmoid with one layer, and it gives us a test accuracy of 88.73%. Then we use with 5 hidden layers, and it gives us a better accuracy, that's 90.68. And when we use the sigmoid function with the hyperbolic tangent and one hidden layer, the test accuracy increases to 93%. Then when we use Keras on TensorFlow, the test accuracy is 98.09% to be ReLU. This is visualization of the loss and the accuracy of the 3D model. The visualization of the loss and accuracy for the 4 hidden layers. CNN, convolutional neural network. That's what we use to get the highest accuracy. So
like layers, as in trying to get stack of layers. While using the convolutional layers, the max flow, then the fully connected layer and the output layer, then it predicts. So this is just an example of what the CNN looks like. Okay, this is a convolutional layer. Taking for example, we have a 5 by 5 input and a 3 by 3 filter. So this is how it does the convolved feature. It takes the 3 and does a dot product on the 3 and keeps moving on the stride of 1 until it does for the row side and then goes for the columns. So it comes out with 5 by 5 and it gives us a 3 by 3 convolved feature. Okay, fine. This is just more like the visual part of what the convolutional neural network does. So it just goes round and it brings out an output. The next slide. Okay, this is how to calculate for the layers to be used. You have an input of n by n, a filter of f by f. This is the output formula. So let's say, for example, we had a 5 by 5 and 3 by 3. So you do a 5 minus 3 plus 1. And 5 minus 3 plus 1 is 3. And by 5 minus 3 plus 1 is 3. So you're having a 3 by 3 convolved layer output. Next slide, please. Okay, fine. We introduce the ReLU after the convolved layer. So the ReLU takes non-negative values, makes it 0, and the positive values calls it the output. So this is what from the one you got from convolved, this is what it is. So you have the only non-negative, and this is what the feature looks like. Okay, fine. We'll go to the pooling layer. There are different types. You have the max, you have the average, you have the sum. But from what we got to know, we found out that the max was mostly used. And what it does is that it takes in a rectified feature map. This is a rectified feature map. So it takes a 2 by 2. It takes the highest, the maximum number in this 2 by 2. So you have 1, 5, 1, 6. And 6 is the highest. It takes that. You go to the next one. So until it does the maximum, that's how it gets to this. And also, we'll come to the final part, taking it to the fully connected layer. First thing first, it flattens what comes out in the max pool, and so that it can be able to feed it to the fully connected layer for it to be used. So this is how it happens. So we use ReLU for the first fully connected layer, and at the end we use the softmax. So in the softmax, you will have probabilities of the classes, how many numbers they are, but everything is still going to sum up to 1. So from here we can see that we have 0.02, 0.94 and all that. So if you sum everything, it's still going to give you 1, but the highest one is this. So you can see that if a boat was the input, it's giving us a boat of this probability, and it's quite correct. Okay, so fine, this is putting everything together. By the time you finish doing the forward propagation, it goes back and does a backward propagation until the weights are able to, until it updates the weight so that we can get a good accuracy and a low loss. So fine, so this is how everything about the CNN goes into play. We initialize all the filters, you go around and repeat this process until you get a better accuracy. Okay, fine. I still got to understand that there are learnable parameters in the CNN. So if you want to get the total learnable parameters in the CNN, you're going to calculate it layer by layer. First thing first, the input layer doesn't have any learnable parameters, and learnable parameters are the weights and the biases. So it's only found in the convolutional network. So from our code, we're using a 3 by 3, 32 channels, that's 3 by 3 filters and 32 in number. So you're going to have, the formula is going to, input number times output plus bias. So we're having a 32 times 3 by 3, one input, and this it gives us this 320 for the first convolutional layer. Maxpool doesn't have a learnable parameter, so it does that till you're able to get everything. And when you sum everything up, you can know the learnable parameters that were used in that convolutional network. Okay, fine. So we'll run our CNN with Keras. We're able to get 99.17. Okay, we're able to visualize it too. And that's the end. Thank you.
What was the architecture you used for this CNN?
That's your house, sorry.
Okay, so like, how many convolutional layers and how many fully connected layers?
Okay, we use three convolutional layers and two fully connected layers.
And you used Keras.
Yes.
So mean accuracy was 98, right?
Yes.
Then test accuracy
99.
Okay. Nice.
There are any more questions? Sorry? Okay, the challenges. Okay. Actually, there is a story, but I'm not going to tell it because it's a good story. But I'm grateful for the people I had. They were good and they were still not good at the point. But the thing is that one person will show up and stop showing up. The next person will pick up from there. So it was interesting, like, we actually have one person that is going with it, but not everybody had to go. So by everything, we were still together. And this morning, we are still representing. Thank you. And we won't listen until you see now. Okay. I think that was all.
Wait, sorry, is this your group? Yes.
Yeah.
Are you full? You said you used Keras.
Yeah, that
No, at the end.
I think
that's
All right, thank you.
okay, so please could we have the next group? Number 2, please. Okay, so we have group 4 next. Please could we have group 4 out to the presentation stage, please?
That will be an issue initially.
Morning, everyone. So we are. We are members of the forum, and we are here to present our project, which is an image classifier using TensorFlow and Keras. And we're able to get good results. So this is, like I said, an image classifier that identifies fashion items just by, like I said the other time. So it identifies the image, and there are so many applications as well. So what we did was that, what was suggested was that we use a fashion image data set to train the data set, the model, because it's a widely used data set for image recognition. And the way it's formatted, it's a 28 by 28 pixel, 70,000 graceful images, 10 categories. So we applied a convolutional neural network to do that. And then my colleague now will take you through the process of which we explore the data sets and train it. So Thank you. Good afternoon. So this is a project objective, as I already mentioned, network, computational network, classify and identify images. So